This problem reads, pipe A, which is 1.2 meters long and open at both ends, oscillates at its third lowest harmonic frequency. It is filled with air for which the speed of sound is 343 meters per second. Pipe B, which is closed at one end, oscillates at its second lowest harmonic frequency. This frequency of B happens to match the frequency of A. An x-axis extends along the interior of B with x equals 0 at the closed end. So how many nodes are along that axis? What are the smallest and second smallest values of x locating those nodes? And what is the fundamental frequency of B? All right, so from the slides or from the textbook, we have a little bit of information that will help us on this. Number one is when you have a pipe of some length L that is open at both ends, the frequency of the harmonic modes in there is given by any integer value n times the speed of sound v over 2L, and n can be 1, 2, 3, etc. If you have a pipe that is closed at one end, also of some length L, the frequency here, pretty similar, n times v over 4L, but here the n's are just the odd integers, so 1, 3, 5, 7, etc. So what we know here is that when we are in the third mode for pipe A, which would be when n equals 3, that the frequency that is produced matches the second mode for the closed open pipe. But the second mode also actually has n equals 3 right here. So there's a couple of different ways you can do this. I'll show you the long way and then the quick way to do this. So first would be to just say, let's just worry about pipe A. So the frequency of mode 3 in pipe A is going to be 3 times the speed of sound divided by 2 times the length of the pipe. And if you push that into a calculator, you get almost 429 hertz. Whereas if you then take that frequency and say, okay, well, I know that the second mode, but it actually is n equals 3 for pipe B because of the odd integer rule, is going to be 3 times the speed of sound v over 4 times the length of the pipe, and we want to solve for the length of the pipe. Well, then we can say the length of the pipe is 3 times the speed of sound, which is 343 meters a second, over 4 times this same frequency, right? We're producing a matched frequency in this pipe. And if you push all that into a calculator, you will find that the length of pipe B is half of the length of pipe A. It's 0.6 meters. There's a quicker way you can do it, though, if you set both of those things equal to each other. In other words, if you say that whatever the counting integer is in pipe A times the speed over 2 times the length of pipe A equals whatever the counting integer is in pipe B times the speed over 4 times the length of pipe B. Well, the speeds of sound are the same. And because of the counting rules here, right, this is all integers, this is only odd integers, NA and NB are actually equal to each other. And so you really just end up with the expression that the length of pipe B is 1/2 the length of pipe A, which is 0.6 meters. However we get that, doesn't matter, but we have that, and so now we can be a little bit more definitive about our pipe B here. So there it is, and then in here is an x-axis that extends along the pipe. There's your x-axis. and the whole pipe right here is 0.6 meters long. So where do we need nodes here? Well, you get antinodes in terms of particle movement at the end and at the open end, and nodes at the closed end. And if you are in the second mode of oscillation, the little wave that gets superimposed over it looks something like this. There is a node right here, a node right here, and then an antinode here and an antinode here. Again, this is trying to not tell you that things move up and down in this pipe, but rather that at this point air particles are moving back and forth a lot. At this point, air particles actually don't move. Back over here, air particles are moving back and forth a lot. Here, air particles don't move. If you were to graph pressure, it would be the exact opposite of here. Here, the pressure is staying the same. Here, the pressure is oscillating the most. Here, the pressure is the same. And again, here's another place where pressure is oscillating the most. So how many nodes are along the axis? Well, if we're in the second mode here, then the answer to this is there are 2 nodes within this pipe. Where is the first one? Well, the first one is at the origin of the x-axis, so it's at x equals 0. Where's the second one? Well, if you just look at this geometrically, it would have to lie 2/3 along the length of this pipe. So the second node lies at 0.4 meters. And finally, what is the fundamental frequency of B? Well, we know that the frequency of B in the second mode is this 428.75, but what is it if we find it in the fundamental mode? Well, we can just do that by plugging in 1 here. We got 343 meters a second over 4, and we know the length of B's pipe is 0.6 meters. And if you calculate that, you get about 143 hertz, which is 1/3 of the value up here. And again, it should be given that the frequency from the base frequency, then you have 3 times, 5 times, 7 times, etc. for the frequencies of all those harmonics. The second problem in this section on sources of musical sound, the group problem that we did not get to in class, reads, in pipe A, the ratio of a particular harmonic frequency to the next lowest harmonic frequency is 1.2, and this was a typo on here, so my apologies. This should just be 1.2 and 1.4. If you actually use the colon as the ratio, it turns out to be impossible to solve this problem, so that's my bad on the typo that was provided there. So again, it's going to be helpful to remind ourselves that when we have open pipes of some length L, the frequencies for these modes are given by NV over 2L, where N is 1, 2, 3, any integer. Whereas if we have a pipe that is closed at one end, but still L long, and the L's don't have to match, the frequency of its harmonic modes is given by NV over 4L, where N is 1, 3, 5, etc. So I think it's easiest to see these ratios if you just write out things in the pattern right here, right? So let's just do open, open, and write out the first few of these. So the first frequency is going to be 1/2 V over L. The next one is going to be 2/2 V over L, or just V over L. 3/2 V over L. 4/2 V over L. 5/2 V over L, etc. So the ratio here of the lowest mode and then the next highest mode is actually a ratio of 2:1, or written in decimal form, just 2, which clearly doesn't match either 1.2 or 1.4. The next one, though, is a ratio of 3 to 2, so that's 1.5, and we're getting closer to both of those values, but that doesn't match any. If you look from the third to the fourth mode right here, that ratio is 4 to 3, or 1.3 repeating. So we've passed this option, but we're not yet past that one. The next one on here is 5 to 4, so that's 1.25, still above that, not quite there. But if we write the next mode in here, the ratio of the frequency here to the ratio of the frequency here is 6 to 5, which is indeed 1.2, and that would tell you that if you have pipe A, which produces this ratio of frequencies of 1.2, it would have to be, how many open ends on there? There are 0 on there. Secretly, you could also argue that it was 2, because the wave patterns within a closed pipe actually match those within open. If you do open closed, same kind of argument here. So the first pattern is at 1/4 V over L. The next one is 3/4 V over L, 5/4 V over L, 7/4 V over L. And the pattern continues. So the ratio right here is 3 to 1, or just 3. That's not going to work. The ratio right here is 5 to 3. So what is that? 1.6 repeating. The ratio here is 7 to 5, and that in fact is 1.4, which is the thing we were searching for pipe B. And what that means is pipe B has one closed end to it.